This week we are going to discuss quantum key distribution.
So what does the protocol for quantum key distribution, QKD, actually look like?
So we have our usual protagonists, Alice and Bob. They trust each other, but they don't have access to a secure channel using which to communicate. They know that any messages that they might exchange in between them could potentially be intercepted by a malicious eavesdropper, Eve or Evan.
What's special now is that in addition to their classical authenticated channel, Alice and Bob have a quantum communication channel. They can send qubits to each other using photons.
But of course, Evan might still be listening in and potentially intercept any qubits that they send to each other. And there is no limit to the power of Evan. You can imagine that he even has access to a quantum computer and can perform any kind of operation that he wants on the qubits that he intercepts.
So let's see how such an attack by Evan might look like. Whenever I send the qubit to Bob, Evan might try and intercept it. And I might not even know about it.
Bob still receives a qubit, but now that qubit might be entangled with Evan, and not just with Alice. Alice and Bob can perform a simple test to check whether their qubits are still maximally entangled,
or not.
So what are we trying to achieve here? The end goal remains the same. The first thing that we want, of course, is for the protocol to be correct. So what this means is that whatever happens, except with tiny probability at most epsilon, the key Ka that Alice obtains should be perfectly identical to the key Kb that Bob obtains.
So how about secrecy? This time, we have no guarantees coming from some special channel connecting Alice and Bob. However, the fact that we can send qubits to each other saves us. You can think that while previously we used the properties of the special channel to obtain a guarantee about Evan's min entropy, this time we can use properties of quantum entanglement to measure the min entropy ourselves. And of course, you've already learned that whenever we know something about the min entropy, we can use privacy amplification to obtain a key.
So we'll quantify secrecy in the same way as we've been doing so far. Eve should be ignorant about the key K. What this means is that the joint state of the key and of the eavesdropper's system E should be close to a state that is in a tensor product, uniform for the key, and perfectly uncorrelated from the eavesdropper's system E.
And of course, at the same time, we would like for all of this to be efficiently implementable so that Alice and Bob can produce key within a reasonable time frame.